Now for the second example here, it's always the same. We are looking for all the eigenvalues and all the corresponding eigenvectors, this time for this 3 times 3 matrix given here. And as you know, it's usually not to be recognized at first sight whether such a matrix is regular or singular or whatever special attributes it has. This is not so important also to this end. We just use our standard method. So I write it down again. This is our matrix. And then we just use the same method as before. So determinant A minus lambda times, I will correct this again, times unity matrix or unit matrix. So this is, as always, the result of this operation is just to subtract lambda on the full diagonal. So on every diagonal element. That's all. Okay, see, minus lambda, minus lambda, minus lambda. Now, so this is a case for example, for the rule of Saros. Saros rule is quite comfortable to use for 3 times 3 matrices. So I will do so. And also what you see is generally the polynomial that will result for lambda is of course always of the same grade as the dimension of this matrix or this vector spaces. It must be, because lambda appears on each and every diagonal element. And if we multiply all these, we get the highest term we get is lambda to the power of 3. So that's no surprise also, yeah? So I just write it down. 1 minus lambda here times minus 5 minus lambda times 4 minus lambda. And then we really have to be careful not to make any sign mistakes. So this is important for you in the exam. If you understood everything perfectly, and then, but you're not careful when just transforming your findings, your equations, you make a sign mistake and then another one, and then you lose your credits, your points. That's just, well, it shouldn't happen, possibly, okay? But you know, it can happen. So just try to be careful. So that's the first, and it's the main diagonal product. The first one that counts positive. So for, as you see, I have abbreviated the Saros scheme. I should have repeated this first column here and the second column here. So I didn't do this, I just put some dots here, but I will then try and jump to the right place. You know what I mean? So let's do it. I take the product minus 3 times 3, and then I must go here, but this corresponds to this, okay? So it's minus 3 times 3 times 6. I jumped over. That's oh, sorry, it's this one. Here I am, the second positive contribution. And the last one then must be, well, there should be another line here. This is just for orientation, of course, yeah. And then, so I take 3 times this means this times this. So 3 times 3 times minus 6. You can do it your own ways, okay? I just use this short representation here. And then now we still need our negative contributions with a minus sign before them. That's what I mean. So we multiply 3, here it is, times this in parentheses, minus 5 minus lambda times 6, and then a minus before it, don't forget. The next one, I go from, how do I do it? Yeah, okay, I would start here, but this corresponds to this element. So it's 1 minus lambda times 3 times minus 6. This is this one, but also a minus before. Important, okay, remember from the scheme here. And then the last, the last one would be this. I start here, which corresponds to minus 3, and then this one corresponds to 3. So it's minus 3 times 3, and then also times 4 minus lambda, and a minus before the whole product. So that's all we have. Now, it's mainly, it's just plenty of work. It's not really difficult, but it takes a while. That's the bad news, okay? So I did the following. I collected all the terms. And as you see, this is quite a step from here to there. Let's try and make it together just shortly. I picked out the highest order terms first, okay? I'm looking for all the contributions which contain lambda to the power of 3. So, but there can only be one, because the only diagonal on which lambda appears 3 times is the main diagonal. So quite obviously, I have minus lambda times minus lambda times minus lambda, which results to minus, stays, okay, minus lambda to the power of 3, minus lambda cubed. That's it. So then I look for all the squared contributions, and that's little, well, you take your time and do it by yourself afterwards, because now it would consume too much time. And perhaps just in short, here I have 1, taking the 1 time, and then times minus lambda times minus lambda. This always, if I combine this with itself, it always results to lambda squared, okay? So I would have 1 times lambda squared, but also minus 5 times lambda squared if I take minus lambda from the other parenthesis. And also additionally 4 times lambda squared. You see what I mean? So I just add these numbers here. 1 minus 5 is negative 4, plus 4 is 0. So in the end, from here, I get 0 times lambda squared. So there's no squared element in the polynomial here. That's all I do. So it's actually relatively easy. Also, I collect my linear terms from here. Here I don't, oh yes, I must be careful, because 1 times minus 5, that's minus 5, and then times minus lambda is 5 times lambda. And then collect again, and also here, minus 3 times minus lambda times 6, and so on. So there are many of them. 1, 2, 3, 4, 5, should be 6 contributions. And if you carefully put them together, you find a positive coefficient of plus 12. So it's 12 times lambda inside the polynomial. And also look for all the constants. It's 1 times, let's check this perhaps. 1 times minus 5 times 4. This should be negative 20. And then plus, if you look here, negative 54 is what I see. But then again, minus 54, you know, 6 times 9 is 54, okay? So that would be already negative 108. Additional to this, whoa, what was it? Negative 20 would be negative 128 as far as I get it now. Then also here, multiplying, minus 3 times minus 5 is 15 times 6. So that's another 90. Here, then this is negative 18. No, there's a minus before. Careful, yeah. So it's positive 18, and then also did I take this into account? This minus sign? I'm not quite sure. Yeah, I should. It's positive. Sorry, it's positive 90. What I get here. So if I remember correctly, let's just check it. All together, I would have minus 20, minus 54, minus 54. This was from here. This was from here, here, and here. And then I would get positive 90. Also, then you can help me if you find a mistake. I get positive 18 and 3 times 6, okay. And then also minus times minus is plus 3 times 3 times 4. So that's another 9 times 4, 36. So if we look carefully, we have negative 128, and we have positive, this is 108 plus 36, as I see. Is that right? Yeah. So it's, help me, what is it? Plus 108 plus, I'm just looking if anybody's awake. What is it? These three together?
Well, I have the same result as you did.
Okay, fine. So I just wanted to know these. It's 144, right? Should be. Yeah. And then if I combine these two, if I subtract this from there, it's exactly, is it 16? Yeah, it's exactly positive 16. So that's correct. And I promise you also this is correct, but you would have to collect all the linear terms here. You see, in the first line, it's just plenty of work. and you should be careful with the signs. Aside from this, if we found, now this is a nice case again for, I just like it, as you know, it's a cubic polynomial. That's, of course, so it's not the classical Vieta's theorem, but you could say the extended Vieta's theorem could be used. And it turns out, luckily, that all the zeros of this polynomial are whole numbers. And now you could guess, okay, you could guess that since 16 is 2 to the power of 4, it might be 2, 2, 4, something like that. 2 times 2 times 4 is 16, okay? And then you would look for the mixed terms, but that's a little more, well, it's a little more complicated than the classical Vieta's theorem. Of course, you can do anything. You can guess the, you know, if you guess, you will find -2, -2 as the simplest solution. Let's just do it. -2 inserted here. So I have -8, which is 8. 8 minus 24 is -16, plus 16 is 0, so it fits. And then you could do the usual thing, performing a polynomial division, okay, or using the Horner scheme if you want. So you could divide this linear factor out of the polynomial, and then the remaining quadratic polynomial has 2 more solutions. These could be found easily by Vieta's theorem, by the way, which are again -2 and +4. So do it the way you want, but easily we find this is the full product form using linear factors corresponding to this polynomial. It makes sense to take the minus outside first of all, and then you will find it's perfect, okay? So what do we have? We have, again, a double solution, which is, you could say, an eigenvalue which has an algebraic multiplicity of 2. This is what I should say, okay? The algebraic multiplicity of this eigenvalue is 2. It's a double solution due to the square here. But we find another simple eigenvalue with a multiplicity of 1, which is equal to 4. So I number them like lambda 1, 2 equals -2, and lambda 3 equals 4. That's just now my numbering. But now it's interesting to see whether this time the matrix has a so-called eigenplane, which is a 2-dimensional eigenspace corresponding to this double eigenvalue. And as I told you before, it's possible that eigenvalue with a multiplicity greater than 1 also has a correspondingly manifold eigenspace, a higher dimensional eigenspace. In this case, we will find, yes, it's true. The geometric multiplicity of the corresponding eigenspace is exactly the same as the algebraic multiplicity. But as I said before, this must not be the case. And no, sorry, it need not be the case. This is what I wanted to say, okay? It may be, but it also may not be. So, and in this case, we expect another linearly independent direction of vectors, which corresponds to an eigenline. So you would say one more simple eigenvector corresponding to this eigenvalue. As I must always say, if we talk about one single eigenvector, we always mean a full eigenline. So that, because that's what we are doing here, is looking at linear maps by applying matrices to vectors. So it's always the case that if you find an eigenvector, that all multiples of this vector are also eigenvectors to the same eigenvalue. So that's just a basic fact behind. Okay. So now let's do it. Let's insert this -2. This time, again, I should write I here. And it's like, I think that's the funny part. It's always nice to see, if you look at the matrix, it looks rather irregular, or numbers not really in any way striking. But if you insert a found eigenvalue, it changes, usually, it changes at once to a matrix which has twice the same row or even multiple rows of each other. And so it's quite easy then to bring it to the into the form of the general solution. So look, I just subtract -2 here on the diagonal, and that's why I add 2. Okay, it's at this place. If I subtract -2, I can also add 2. So 1 plus 2 is 3, -5 plus 2 is -3, and 4 plus 2 is 6. And suddenly I have first and second row identical, and the third row is even the almost the same again. It's twice the second or first row. So that means all at once, without using any Gauss or Jordan elimination, I can cross out both lines. You know why? Because quite obviously I could add these 2 rows so that a 0 row appears, and a clean 0 row, I must say. So perhaps it's better to do it this way. And also I could add this row times 2 to this one, and I get another 0 row. So actually, I would not really cross them out, but I would just replace them by 0 rows, or both of these, okay? Since this is so obvious, I don't even write it down, okay? What I do is I just focus on the remaining equation. So now, but this is what you should know and remember from our topic, solving SLEs in general, okay? Systems of linear equations. So what I do is I choose those 2 components which have a 0 row corresponding to them. I chose those 2 components to be some parameter. In this case, the second one is called U, the third one is called V. This is just my choice. Okay, so these are solution parameters. Then I insert them into the remaining equation. So if I read this out, I would get 3 times x1 minus 3u plus 3v equals 0. And then I put these 2 terms to the other side, and then I divide everything by 3, and suddenly I get that x1 equals u minus v. That's all. And if I get this, this is it. So this is the general solution to this homogeneous SLE. And this is already the set notation. So it means every vector of this kind where u and v element r is a valid solution. On the other hand, it means suddenly that we have a whole plane of vectors represented by this solution set. You see? And I must add, should be written here, well, I put it below, that the pair UV must not be 0, 0. You know, this is important. It means we want to exclude the 0 vector again, but be careful. It's not forbidden for u to be 0 or for v to be 0. It's just forbidden that they both get 0. Because in this case, we would have 0 also here and then 0, 0, 0. Yeah. So it's always about the question how to exclude the 0 vector, which should not be taken as an eigenvector. But if you don't see clearly that this must be a plane described by this set, it's perhaps, it helps you to put it in a little more familiar form, which you know from school, from the topic of analytical geometry, where you talked about the parameter form of a plane equation with 2 parameters and two direction vectors spanning this plane. You know what I mean? You remember? Secondly, it's quite obvious that since we are looking at linear homogeneous situations only, for any eigenvalue problem, the corresponding eigenspace must run through the origin of the vector space. Although the 0 vector is always excluded, anyway, any eigenline or eigenplane or eigensubspace always includes the origin. It must, because of the homogeneity of the whole operation that we are looking at. Okay, so that's easy to say. We take the 0 vector as a starting point for this to describe this plane. But now look what I do. I extract. You could say I take the factors of u inside this resulting vector. So this is 1 times u, 1 times u, no times u. So it's like 1, 1, 0 times u. Okay, putting pulling u outside the parentheses. Plus the next contribution, factors of v, it's factor -1, factor 0, factor 1. I mean, -1v 0v, 1v. So it's -1, 0, 1 times v. In the end, I have, look at this. These are the two, as I said, direction vectors spanning this plane. They are linearly independent, as you see. They do not point in the same direction. So they do span a plane, which is the solution plane. These are the freely chosen solution parameters, also for the plane equation in parameter form. And this is the starting vector. So that's absolutely clear that this is an eigenplane, a 2D eigenspace. That's what I wanted to tell you. And now what we found is we have, in this case, we have two linearly independent eigenvectors for one of these eigenvalues. But exactly speaking, if we find two linearly independent eigenvectors to one and the same eigenvalue, they suddenly represent a whole eigenplane. Because if you take linear combinations of two, just imagine you would find two eigenvectors by chance which fulfill the eigenvalue -2, and then you would take any linear combination of these, and due to the linearity of everything we are doing here, you will find that the new vector again is an eigenvector to this eigenvalue. So it's no surprise that we have a whole plane of eigenvectors. So, but this can only happen if you have an eigenvalue with a algebraic multiplicity of at least 2. And in this case, we have a double eigenvalue, algebraically speaking, okay? And as we see, also the geometric multiplicity in this case is exactly the same. It's 2. On the other hand, this is what's missing here, is it? No, it's not. Yeah, just as examples for these two, as examples for valid eigenvalues, I can take just these two. For the remaining eigenvalue λ3, we would expect at most to find another direction which is by guarantee not lying inside this plane. Otherwise, it could not belong to a different eigenvalue, which is 4. Okay, so it would have to be something like, you could say, a line through the origin which intersects this plane in the origin. And this is what we find: one single, one-dimensional eigenspace for the other eigenvalue. Let's do it. We insert, what is it? A 4 here on the diagonal for us. By subtracting it here, here, here. 1 minus 4 is -3. Here we get -9, if you follow me. And 4 minus 4, this should even be 0. So if you look here, that's it, -3, -9, 0. That's our resulting matrix. Now this time, we do not see at once that there will be a 0 row. So what I did is I just started out doing, I think, simple Gauss elimination. You see what I do? I mark this diagonal element starting in the upper left corner as always. I add this row to the second one. Here I get 0 by eliminating. Here I get -12 in sum, okay? And here I get 3 plus 3 equals 6. And I do quite the same here. I add the first row times 2 to eliminate here. So 6 plus 2 times -3 equals 0. Then -6 plus 2 times -3. So it's -6. -6 is -12 again. And 0 plus 2 times 3 is 6. So you see, suddenly the second and third row are identical, and we can almost stop the procedure and replace this by a 0 row, because that's a nice point. We can be very sure that exactly 1 0 row will appear, not 2 of them. 2 of them would mean another eigenplane, but you all know it's impossible to find 2 eigenplanes for 2 different eigenvalues in a 3-dimensional vector space. You will never find 2 planes in 3D which do not intersect. So that's or which would just intersect in the origin. Instead, they would intersect in a whole line, and this line of vectors would then correspond to 2 different eigenvalues at the same time, which is a contradiction. Okay, so this cannot happen. Also, our eigenvalue 4 has turned out to be a single solution of the characteristic equation, okay? And a solution with a multiplicity of 1, algebraic multiplicity of 1, can never have 2 or more dimensional eigenspace. That's just some basic facts behind. So then what do? I divide this equation by 6, so that it's a little simpler then with also, okay, I see. We must go one step ahead in order to find our clean solution. That's true. So let's just do it. I divide this by 6. I get 0 minus 2, 1. And then I would, it's a little work to do. I would add this row to, okay, I take this one, this first row times 12, and then I subtract the second row. You see what I do? And here, I just subtract the second row. So that's easy. That gets my 0 line. But up here, you will see the following. This times 12 is negative 12 minus 0. So originally, this would be negative 12. Just remember for a while. Okay. This one, minus 1 times 12, negative 12 minus negative 12 equals 0. And here, it will be 1 times 12. So 12 minus 6, which is 6. So in the end, I would have negative 12, 0, 6, and then dividing by 6. So that's, perhaps I should put this here, that then afterwards, I would divide the whole row by 6, and then I get my simple result. So what do? As always, now I use the same symbol as above, but of course this should not be the same u as here. It's just a newly chosen solution parameter, okay? So I choose my third component to be equal to u firstly, and then I would read out the other 2 lines, which now say that minus 2 times x1 plus u would be equal to 0. And then isolating x1, I would get a fraction on the other side. And to avoid this fraction, this is, you could say, sort of a trick that I use. To avoid this fraction here and also here, I decided afterwards not to set, let's just put it here, not to set x3 equal to u, but actually equal to 2 times u. You know that u is freely chosen anyway, so I can call it u or 2u. I can do what I want. Okay, so that's allowed. And if I do it this way, and then if I read out this line, it would read minus 2 times x1. This goes away. Plus 2u is equal to 0. And you see now I can divide by 2 and isolate x1, and I get x1 equals u. And also much the same here. Here I get x2 equals u if I fill in x3 and then isolate x2. So this is just standard from solving systems of linear equations. So in the end, I get all vectors of the sort u, 2u with u element r excluding the 0. So again, it makes sense to to write down an example of this kind of eigenvector, which would in this case be just a simple choice of u. I would recommend to set u equal to 1, and then you have 1, 1, 2. So this is a good, let's say it's a representative of all these eigenvectors, okay? Also, this is for your information to see that this is exactly an eigenline, that this is the equation of a line in parameter form. Oh, I said plane equation. No, sorry, there are some mistakes inside the solution. It should read line equation at this place. Yeah. Now, so that's an example eigenvector. In the end, we have a full coverage of the whole vector space with eigenspaces. That's important because under this condition, it is possible to do a certain transformation which transforms our matrix to diagonal form. And this is, well, I don't know what's the official name, but probably it's called the diagonalization theorem. And I'm quite sure, I know it, that Martin talked about this, and it's written in your script. But possibly you didn't spend so much time on it. If you remember, you just look it up. please do afterwards. Look it up in the script. You will find a theorem which states that in this way, by multiplying with a certain transformation matrix B from the right side and with its inverse from the left side, it is possible to transform the matrix A to a diagonal matrix. And the fascinating thing is there's a very easy recipe to find this B matrix, transformation matrix, and also the diagonal matrix, which contains all the eigenvalues on its diagonal in the end. Perhaps now you remember what I'm talking about. The most, you could say, the most difficult part here would be to transform, to calculate the inverse matrix of B. So the inverse of the transformation matrix, B to the -1. That's a little bit of work, but this is always the same, as you know. It's the usual method by using the adjoint matrix, etc. Yeah, this method with minor matrices, etc. But this is not what I wanted to emphasize. I just wanted to inform you that we can use this theorem now, since we found that the full vector space is covered by eigen spaces. Now, you know what I mean? We have an eigenplane plus an eigenline. So we have dimension 2 plus 1 is 3. And so the full dimension of the vector space is represented by eigenspaces, one plane, one line. And under this condition, it's always possible to make this transformation. Please don't be confused if you see that when I say transforming the matrix A, that I do a transformation from both sides. That's part of the basic theory of matrix algebra. Okay, so it's always necessary then to transform, if you want, from both sides exactly in this way. And now the two aspects are very nice to know. The first one is what I told you, that in the end, exactly the eigenvalues will be on the diagonal. The second, or you could say the first aspect, is that the B matrix is easily constructed by just, you see what I'm doing? Just putting all the eigenvectors that we found one by one next to each other as columns. And in this way, constructing the B matrix. And it's guaranteed that this is a valid B matrix. And if you use it here and it's inverse here, you will by guarantee transform the matrix A to diagonal form where its eigenvalues are on the diagonal. You can do this and check it, and you will find it works. Why do I use these three? Just remember, for the eigenplane corresponding to eigenvalue -2, I use these two vectors, examples to this, okay, which are 1, 1, 0, -1, 0, 1. Here. Okay, they are behind, sorry. 1, 1, 0, no. Okay, I just exchanged them, but that doesn't really matter. -1, 0, 1, 1, 1, 0. I must admit one should take a little care for this to be a right-handed system of basis vectors, perhaps. They span the vector space, you know, but that's not so important now. And this one, 1, 1, 2, is the one we just found here for eigenvalue 4. So if we use them in this order, we can also expect the eigenvalues to appear in the same order, corresponding order, you know? So this would mean, this corresponds to eigenvalue, the eigenvalues I wanted to say, yeah? Eigenvalue -2, 4. So we would expect to appear -2, -2, 4 on the diagonal elements. As you will see, take your time to go through this. In the end, by constructing the matrix B inverse, which is this one in the end, it's, you know, it's plenty of work, but we've done this last time. We trained this method, and so I don't want to do it again. So this will be it, and then multiplying this to this, what I told you, to matrix A, and then times our B matrix, which we constructed using the eigenvectors of A, and then doing the, well, this is a little bit of work, of course, doing the using the Urtic principle, row times column, every combination here and here, and you can use the associative law, so you can as you want. I would start here. I would do this first. This is an intermediate result. And then if I multiply this one with this in the end, I get exactly the matrix -2, 0, 0, 0, -2, 0, 0, 0, 4. Here are our eigenvalues on the diagonal. So you believe it. You see that it's true, and you can go through the calculation step by step.